All right, let's take a look at unions. We'll see that a union is a way to circumvent C's type system. In particular, it allows you to look at the same extent of memory using different types. And although they look similar to structures and are often covered at the same point in a course about C, they're actually very, very different. So just for reference, here's a structure that is just got three simple elements inside of it: a character called C, an array of two integers called I, and a double. And I've defined an instance of this called SP. Now, here's a union that has exactly the same elements within it. You can see it's declared a little bit differently here as a union instead of a struct, and I've given it a different name and declared a different pointer to it. Now, let's look at what these are structured as under the hood. So this is the layout of the structure, as you won't be surprised to see. We've got a character at the beginning here corresponding to this first element. Then we have to skip some bytes to get to an integer alignment location, and then we can store the two integers in this array. That only brings us up to an alignment of 12, or an address offset of 12. We're not aligned on an 8-bit boundary, so we've got to skip 4 more bytes, and then we can store our double. So that should all be familiar to you by now. Let's see how the union is laid out in memory. As you can see, it's very different. In particular, it only occupies 8 bytes. And you can see that the way that I've drawn this here shows that the character C and the first byte of the first integer in the array and the first byte of the double V are all actually at the same address. And the overall size of the union is basically just going to be the size of the largest element within it. The idea here is that we could read or write from this same part of memory using any of these three data types. I could write a character and it would be stored at this location, which if I read it back in from this 0th element of array I, the first byte of that integer would actually be the same byte as that character that was written. So they're actually overlapping one another in memory. Why in the world would we want to do this? Let's say we wanted to declare a structure that would allow us to store a binary tree. So here's a structure that's got 2 pointers in it to a left and a right child, and the data payload in each of these nodes is going to be an array of 2 doubles that's just called data. Let's imagine furthermore that the requirements for this particular binary tree are that the interior nodes of the tree will never have data. They'll only be pointers to their children, and the only place that the data values are going to be used is at the leaf nodes of the tree. And that basically means that when we're storing information in this tree, we're going to always allocate a left pointer, a right pointer, and 2 doubles, which would be 8, 16, 32 bytes of storage. But in any of those nodes, we would only be using half of that storage. If it's an interior node, we're going to use the left and right pointers. And if it's a leaf node, we're going to just use the data array. And the other half of the structure is going to go empty. So we could use a union to help with this. Here's a union called node U, and it's got 2 elements inside of it. One is a structure that we'll come back to. The other is this array of 2 doubles. Now the structure itself then is really there just to wrap up these 2 pointers, the left and the right portion of the tree. Because the contents of each of the elements of a union overlap one another in memory, we would only be allocating 16 bytes for this union. We've got 2 pointers here, that would be 16 bytes. We've got 2 doubles here, that would be 16 bytes. And those 2 allocations are going to overlap in memory. And that works fine for us in that we're only going to ever store either pointers for interior nodes or the double data for a leaf node. So here's a visualization of that. This was the layout for the structure. From the beginning of one of these structures, we're going to have the left pointer, the right pointer, and then the 2 integers that store the data. So we're going to use 32 bytes of memory for every node, even though we're only going to use either left and right or the data array. In contrast, for the union, the left and the right pointers inside of this structure are going to be allocated in the same memory locations as the double array called data. So these are going to overlap one another in memory, which is going to work okay because based on the definition of the algorithm, we're never going to store both pointers to children and data. So we can use the same memory locations to store one or the other, depending on whether it's a leaf node or an interior node. Now that previous example is a little unrealistic in that we would have to have some way of determining whether the particular node that we're traversing was an interior node or a leaf node. We can't really tell by checking to see if there's a null pointer or something like that, because we're going to literally overwrite the storage for the pointers and the data with one another. So in practice, we're probably going to have to allocate an additional element of this top-level structure that tells us what is the type of this particular node. Is it a leaf node? Is it an internal node? So I've declared a type here called node type T. It's an ordinary C enumerated type. And I've defined two values, n leaf and n internal. And that value is just going to be stored here inside this type element. So that our node now becomes a structure that can contain the type and then the union that's either going to contain the pointers to the children for an interior node or the data if it happens to be a leaf node. And the algorithm will be able to figure out whether it's an interior node or a leaf node. In other words, figure out which of these two overlapping parts of storage to use based on the value of this type element. So although we're no longer saving half the memory by using a structure as we were seeing before, we're still skinnying down the amount of memory for each node from 32 bytes to only 24 bytes in this case. Here's another example. Let's say we wanted to be able to look at the specific contents of a double as we've allocated it in memory, but we want to be able to do it a byte at a time. Now we know that we could use masking and shifts and so forth as we did in the data lab, but here's another way of being able to access that same storage in two different ways. So I've defined a union called aliases because the two elements of the union, as always, are aliases for each other in terms of overlapping each other in memory. And I've got a double called dibble and an unsigned char called bytes that's 8 bytes wide. That's an 8-byte array of chars. And the double, of course, we know is also going to be allocated to be 8 bytes. So these guys are going to overlap one another in memory exactly. Now, I want to make Jonathan Swift happy, right? He was the author behind the notion of big endian and little endian. So if we're going to be able to read things out of memory from an x86 architecture and do it in an order that makes sense when we're looking at a double, we're going to want to be able to flip these bytes around. So this is just a really simple implementation of a little loop that will go over n bytes and flip them end for end. Here's a little test function that's going to let us try out the union that we've just defined. So here's a union aliases that I've just declared. I'm going to call it peak. And the first thing I'm going to do is write into it a double. So back in the definition here, I'm going to write into this element. But because these two locations in memory overlap one another, I'm also writing into this bytes array. So what am I going to write there? Well, I'm going to put this test value in there. I've defined that up here as 1234567 So that's going to take that double value and write it into that location. Then I'm going to print out the value of that double value just so that you can see what it looks like on the console. Then what I'm going to do is I'm going to print out the value of the bytes in that same location. So this is a print bytes function like we've seen a couple times already in the course. I'm saying I want to print 8 bytes and I want to print them from peak.bytes. So although I was able to write a floating point, actually a double value, into peak.double, I'm able to read those same bytes back out by accessing them through peak.bytes. So this is an array of 8 bytes or a pointer to a char, and I want to print out 8 of them. And we'll see what that looks like in a second. Then I'm going to run my little flip bytes function to convert the endianness of the representation in memory. And then I'm going to print the bytes again so that we can see them in the order that corresponds to the way that they're stored in the original double. So here's the output that we get. We can see that our starting value, 1234.5678, that's what we're going to write into the DBL element of the union. And then the original values that get stored in there in order are shown here. And then you can see here the flipped values are in the next portion of the output. And this just switches end for end, AD, AD, FA, FA, down to 4040. Now we can use that little visualization tool that we've been using to see what this actually looks like. So here's that that value, 1234.5678. And you can see here, let me skinny this down so we can see portion of this output. This is going to show up in this flipped order. So we've reversed the crazy endianness of the Intel architecture and printed out the contents of the bytes that got stored. So here's our 64-bit double value, and you can see here that the first byte is 40. Well, here's the first byte, 0100, that's a 4. Next byte 0000, that's a 0. Next byte 1001, that's a 9. 0011, that's a 3. 0100, that's a 4, and so forth. So we're able to see exactly the bytes that we're expecting in the encoding of that double value, and it conforms to our understanding of what it should look like based on that visualization. So again, we're accessing values in memory using different types, even though they're the same bytes in storage. So we had written a double, we were able to access it as bytes. We were then able to manipulate those bytes to flip around the endianness of the representation of this original double, and then access them as bytes to print them out to see what their values are.